Hello and welcome back to the Biochemistry for Health Sciences channel. In the next few videos, we shall discuss metabolism. As a healthcare professional or healthcare student, it is very important that you be able to understand and apply metabolism rather than memorize metabolism. It is also very important that you always consider the big picture when we discuss human physiology as well as human biochemistry, including metabolism. So let's look at the big picture of human metabolism. In a previous video 1.4, we asked this question: what is the most important requirement for survival of a human and propagation of the human species? And the hint was a 6-letter word, and the answer is energy. As we all know, without energy, nothing is going to happen. A cell is not going to survive without energy. A human is not going to survive without energy. We store and use energy in a form of a chemical. The most common is a nucleotide ATP, adenosine triphosphate, but we also use other types of nucleotides, including GTP. So when we use the term ATP, we are really referring to energy. Now remember, as we mentioned in a video much earlier on, the adult human body has about 30 trillion cells. So that's what we are. We contain about 30 trillion cells, of course not including the microbes that are present in our body, but as far as the non-microbial cells, we have about 30 trillion cells. And these cells are scattered everywhere, all the way from the head to the toe. So one of the most important principles of metabolism, one of the most important aspects about metabolism that we should consider is this problem here. How does the body make sure that all your 30 trillion cells from head to toe are able to generate energy at all times? This is important because humans do not store ATP. Okay, so we do not store this energy chemical ATP. We do not store this. So if you weigh 150 pounds, you hardly have less than 1 pound of ATP in your body at any time. Okay, so since we don't store ATP, our cells need to generate ATP at all times. So there are two major ways by which our cells can generate energy. One is directly from a fuel. In this case, we get much less energy, about 15-fold less energy, but this is sufficient for 80% of our cells. So out of 30 trillion cells, the 24 trillion red blood cells, this is enough. Just getting ATP directly from fuel. However, for the remaining 6 trillion cells that are not red blood cells, so the remaining 6 trillion cells, this is not enough. We need to generate much more energy, maximum energy. And this can be done if these cells have fuel plus oxygen. Okay, so we need an additional requirement here, and that is oxygen. So red blood cells do not need oxygen for energy generation. The rest of the body cells do. So these cells need fuel. These cells also need fuel, but they also need oxygen, which is not required for red blood cells to generate energy. So the answer to the question, how does the body make sure that all 30 trillion cells are able to generate energy at all times? The answer is the body makes certain that there is fuel that is given or provided to the 24 trillion red blood cells at all times, and there is fuel and oxygen that is provided to the remaining 6 trillion cells at all times. So this is what the body will have to do. We have to provide fuel to the 24 trillion cells all the time, red blood cells, and we have to give fuel and oxygen to the remaining 199 different types, which are about 6 trillion of them. Now let's assume there is enough oxygen for these 6 trillion cells. Okay, so remember, oxygen comes through the nose, through the lungs, and then into your bloodstream. So let's assume there is enough oxygen. So what we have now is a new problem. So the modified problem now is, how does the body supply fuel to all the 30 trillion cells all the time? So this is the modified problem now. So let's look at how does the body supply fuel to all our cells, 30 trillion cells in an adult all the time. So what is fuel for the body? Fuel is any chemical where you have 1 to 4 hydrogens attached to carbon in the chemical. We call this reduced carbon in chemistry. The two most important fuels for the human body is, one, the most important of all, is glucose, and number two are the fatty acids. Now, if glucose and or fatty acid is insufficient, only then will we use amino acids as a major form of fuel. Okay, so does this mean now that we can give glucose or fatty acids to the red blood cells and glucose or fatty acids to the other non-red blood cells? Unfortunately, the answer is no. Yes, Houston, we do have another problem we have to deal with. And here is that problem. Red blood cells and the brain cells can only use glucose. They cannot use fatty acids as fuel. So now we have this limitation. So red blood cells can only use glucose. Brain cells almost predominantly can only use glucose 80%. They do get a little bit of energy from fatty acids, but less than 20%. So predominantly from glucose. The rest of these cells, the remaining 5.9 trillion cells, they can get their energy either from glucose or fatty acids, whatever is available to them, glucose or fatty acids. So where do these cells get their fuel and oxygen? And the answer, of course, is bloodstream. Your bloodstream connects all 30 trillion cells to basically to one another. So since all cells get their nutrients and oxygen from the bloodstream, this means that the body must always maintain blood glucose concentration at least above 40 milligrams per deciliter to feed the 24 trillion red blood cells and 0.1 trillion brain cells. So this 40 milligram per deciliter is what we call a critical glucose level. So clinically, if your blood glucose falls to around this number, around 40 to 50 milligrams per deciliter, it varies a little bit from hospital to hospital. But around this region, if it falls less than this, then the brain cannot get enough glucose, and we can face very serious consequences, including fainting and getting into a coma. So this means the body must always, whether you are sleeping or you're awake, whatever you're doing, must always maintain your blood glucose concentration above 40 milligrams per deciliter, so that we can provide enough glucose for the red blood cells as well as for the brain cells. So this, my dear friends, is one of the most important programs for human survival, one of the most important programs for human metabolism. Our blood glucose concentration must always be above 40 milligrams per deciliter to make sure your brain cells have enough glucose as well as the red blood cells. If you are interested in learning about the other programs for human health and survival, there is a very nice book, Revelation 2.0, this book here, and you can get it from this link. A human goes through various stages within a day. So when you have a meal, you will get into a postprandial state after you have your meal, for example, your breakfast, and then between breakfast and lunch, you might enter an early starvation state, and then during lunch, you again are in the postprandial state, and between lunch and dinner, once again, you might enter into a early starvation state, and then postprandial for your dinner. And now when you're sleeping for hopefully 8 hours, you are into a early starvation state. So we basically cycle through postprandial and early starvation state during a day. So besides the early starvation program as well as the postprandial program, we do have another program, metabolic program, and this is called the late starvation state, late starvation. And this happens if we do not eat for more than about 24 hours, about a day. Okay, so if you do not eat for more than a day, then we can get into a late starvation program. And this is something more of an emergency program. This is more of an emergency program. So for example, you're hiking in the woods and you lose your way and you don't have any food left and you haven't eaten for a day, then your body will get into this late starvation program. So remember, it doesn't matter what we are talking about, which state, after a meal or early starvation or late starvation, your body must always satisfy this criteria. Your blood glucose concentration, doesn't matter after meal or early starvation or late starvation, this must always be above 40 milligrams per deciliter. Okay, so this is critical. This is very, very important. This is what is the crux of metabolism. We must maintain our blood glucose more than 40 milligrams per deciliter, otherwise your brain will be in serious problems. Okay, so you're including your red blood cells. Okay, so after a meal, postprandial, you just had a wonderful meal. Let's see what happens after a meal. So we have, when we say a meal, I mean a meal that has carbohydrates. Okay, a normal meal. A normal meal means carbohydrates. It has carbohydrates. Whatever it is, form of bread or rice or whatever, there is carbohydrate present. And carbohydrate means there is glucose present. Okay, so you eat your meal, the carbohydrate is broken down into glucose, and glucose will be absorbed into your bloodstream, and it will enter the liver. So once it's in the liver, then of course the glucose, some of the glucose will be used up by the liver to generate its own energy, ATP. Some of the glucose will be used up to replenish any glycogen that was used during when you were sleeping, for example, during early starvation. As we shall see later in early starvation, this glycogen is actually broken down to glucose to maintain our blood glucose concentration. So any glycogen that was used up, this glucose that you get from your diet will be used to replenish this glycogen. Then the glucose will go to rest of the body. In the bloodstream, all the red blood cells can use the glucose that you got from your diet to generate its ATP. In the brain, the glucose again can be used to generate ATP. And since there is quite a bit of glucose, because this glucose is coming from a diet, your carbohydrate diet, there is enough glucose for the adipocytes, the adipose tissue, to generate ATP. And the adipose tissue will also take some of its glucose and it will make it into fatty acids and then eventually into triglycerides. So triglycerides are basically a storage form of fatty acids. Okay, so that's adipose tissue will do that. Glucose will enter the muscle cells, and there glucose again will be used to generate ATP for the muscle cell, and the muscle cell will also use some of its glucose and store it as glycogen. Okay, so muscles do need additional energy and they do store some of the glucose as glycogen. So most of your glycogen, you can see, will be in your liver as well as your muscle. So basically what this means is after a diet, there is a glucose coming from your diet, and that glucose is sufficient to make everybody happy. Your liver is happy, especially your red blood cells in your brain, they are happy because they have enough glucose that they can even share it with the adipocytes as well as the muscles. So after a carbohydrate meal, maintaining blood glucose more than 40 is not a problem at all. In fact, after a carbohydrate meal, your glucose can go as high as 120 to 140 or so milligrams per deciliter. So that gets pretty high, and this is a time, because of very high glucose, this is the state where you see insulin release. Okay, so the beta pancreatic cells, they will release insulin only if your glucose is very high, and that means only after a meal. Okay, so only after a meal, when your glucose is high, that will stimulate release of insulin into the bloodstream. So that's when we see insulin release after a meal. Okay, so what happens, let's say, in early starvation? Okay, so you had your dinner, you went into a postprandial state, no problem. Your glucose that you ate maintained your blood glucose level more than 40 for a few hours, and then you went to bed. Okay, so what happens early in the morning, say let's say around 2-3 p.m. Now you have not eaten for a few hours. So now you get into this early starvation. So once again, we need to ask the question, how do we maintain our blood glucose in early starvation at least more than 40 milligrams per deciliter, so that we can feed our red blood cells and our brain cells? Okay, so this is really the question we need to look at. Okay, so when you are, let's say 2 p.m. in the morning, you have not eaten for some time, you are not going to get this glucose anymore, right? There is no dietary carbohydrate anymore. So the question is, how do you maintain your blood glucose at least more than 40? And the answer is, the most predominant route to do this is using liver glycogen. Liver glycogen is broken down into glucose And this glucose is exported out of the hepatocytes, the liver cells, and that is what maintains our blood glucose in early starvation. Glycogen from the muscles cannot come out into the bloodstream. Okay, glycogen from the muscles will break down into a different form of glucose 6-phosphate, which we'll talk about some other time, and that only stays in the muscles. Okay, so muscles are not very they are not very cooperative. They are quite stingy with their glucose. They only keep it for themselves. But the liver takes care of everybody. It breaks down this glycogen to glucose, and that glucose will maintain our blood glucose more than 40 milligrams per deciliter. So now we have this glucose coming from our liver, and this glucose will now help feed our red blood cells and our brain cells. Now, to make sure that the rest of the cells do not steal this glucose away from the brain and the red blood cells, the rest of the cells start using fatty acids. So the triglycerides in the adipose tissue is broken down into fatty acids. So these fatty acids will provide energy for the adipocytes, and the fatty acids will come out into the bloodstream, and the fatty acids will provide energy to the liver, to the muscles, and to all other cells. And by doing this, the body makes sure that the glucose, that is limited amount of glucose that is coming from the liver glycogen, is being used up only by your red blood cells and by the brain. Good to note that in early starvation, your blood glucose is much lower than postprandial, so there's no more insulin release. In fact, when your blood glucose is very low, not the beta cells, but the alpha cells, the alpha pancreatic cells, they are stimulated to release another hormone called glucagon. So in starvation states, we see glucagon is the major hormone that affects metabolism. After a meal, it's insulin that affects metabolism. Okay, so that should take care of us daily. After a meal, we have our glucose coming from the diet that is going to maintain our blood glucose more than 40. And when we are in early starvation, then it's your liver glycogen that is going to maintain your blood glucose more than 40. And we'll cycle through this early starvation and postprandial states throughout the day. Okay, and so between liver glycogen and the liver glycogen as well as the glucose coming from the diet, we should be able to maintain our blood glucose more than 40 milligrams per deciliter, and we should be fine. So besides the postprandial and the early starvation program, we do have another program, and that is the late starvation program. And this happens if you have not eaten for more than 24 hours. Now, why 24 hours? That's because the average person has sufficient glycogen to maintain blood glucose in early starvation for 24 hours. Okay, so we don't store a lot of glycogen in the liver. We just cannot, because glycogen absorbs a lot of water. If you need to store glycogen for more than a day, then the liver becomes very, very big, and that's not possible. So we do not store glycogen for more than a day, to provide glucose for more than a day, just for 24 hours. So now we have a situation where there is no carbohydrate. You have not eaten anything, so there's no carbohydrate or glucose coming from the meal. There is no more glycogen in the liver, so this is basically gone. Okay, so we don't have this and we don't have this. So now the question is, where do we get this glucose that maintain our blood glucose more than 40, so that we can feed our red blood cells and the brain cells? So the answer to the question is we start making glucose. Okay, so the liver once again comes to the rescue. The liver starts making glucose. But to make glucose, you need building blocks. You need carbon building blocks, especially pyruvate. Okay, so the question is, where does this pyruvate come from? And the answer is the pyruvate comes from protein breakdown. Since muscle contains most of your proteins in your body, so basically muscle proteins are broken down into amino acids. Remember, there are 20 amino acids that make up proteins. These 20 amino acids are basically converted into two types, glutamine and alanine, and these two types are transported to the liver where they are converted into pyruvate. And this pyruvate will be made into glucose, and this glucose is exported into the bloodstream to feed the red blood cells with ADP and to feed the brain cells so that they have enough glucose for their ATP energy. So as in early starvation, to make sure that this glucose, this limited amount of glucose that is coming from the liver is reserved only for the red blood cells and the brain, the rest of the cells continue using fatty acids. They will get most of their energy now from fatty acids. So hopefully this late starvation program will help you. You're lost in the woods hiking, so hopefully it'll help you buy some time to find some food and get back into the postprandial program. However, what if you still cannot find food? Okay, you're still lost and unfortunately you still cannot find anything to eat. Now what happens? So one of the problems of this late starvation program is that we are getting building blocks. So this pyruvate, this building block necessary to make glucose, this is coming from proteins. Okay, it's coming from proteins, and most of the proteins are in muscles, so it's really coming from your muscles, and your muscles are going to start breaking down. The muscle proteins are breaking down, and once, if your muscles keep on breaking down, then you won't be able to move around to find food. Okay, so that's not good, right? We don't want to continue breaking down our muscles. Okay, that will be difficult for us to walk around or run around or climb a tree to find food. So to avoid continuous muscle breakdown, now we enter a later phase of late starvation. And what the liver does now is, besides using fatty acids to generate its own energy, the liver converts some of these fatty acids into these chemicals called ketone bodies. Now these ketone bodies are exported into the bloodstream, and now the brain can use ketone bodies besides glucose. So now the brain has two sources of fuel, glucose and ketone bodies. So now the brain starts using less and less glucose because now it can get its energy from ketone bodies. The red blood cells, however, cannot use ketone bodies. They continue getting their energy from glucose. Now, ketone bodies can also be used by the rest of the cells. So ketone bodies can be used by adipose tissue, by muscles, by liver, or most other cells. The heart tissue, for example, can use ketone bodies. So, and the most important is the brain can also use ketone bodies. So, but red blood cells, the 24 trillion red blood cells, unfortunately, they cannot use ketone bodies. They still need their glucose. So this formation of ketone bodies hopefully will buy us even more time. to find food. And if we still are not able to find food, then it's bad news for us, because that will mean that more and more muscles as well as other proteins are being broken down, and that can lead to serious organ damage and death. So hopefully the late starvation program will buy us time and bring us back into our normal cycle of postprandial and early starvation. So just to summarize, we have three major metabolic programs: postprandial, early starvation, and late starvation, which consists of two phases, the early phase and the later phase. Okay, so besides exercise, which we'll talk about in the future, always remember these three metabolic states that humans go through, and the programs we use to keep us alive, to keep our blood glucose concentration greater than 40 milligrams per deciliter. So please keep this big picture in mind as we go through more videos on metabolism in the near future. So until the next video, goodbye for now and have a wonderful day.